Hello, welcome to our PR 2021 presentation titled Please Hold On, More Time Equals More Patches. In this talk, we are going to discuss our work in progress on evaluating automated program repair tools as anytime algorithms. This is a joint work with Pashchenko and Fabio Massacci, and this research was partly funded by the EU's Horizon 2020 Ashmore project. Let us start discussing several aspects of evaluating API tools. Most of the evaluation methods they focus on the effectiveness of the API tools. For example, counting the number of patches generated by the API tools. While little is known about the practical aspect of using the API tools, for example, by constraining the search space, could also show that the number of patch candidates can vary significantly, which might impact the number of possible patches. Later, Martinez or they show that by giving an additional time budget, we might get a high number of possible patches. The rest all, they studied 11 API tools, and they show that most of the repair attempts that resulted in error or terminated within a timeout. On the other hand, our goal is to investigate how long one needs to wait for a tool to generate a bug fix. To see if it makes sense to wait longer in order to obtain better results. Our long goal is to understand whether API techniques are anytime algorithms. Because by definition, anytime algorithms give intelligent systems the capability to trade deliberation time for quality of results. In our context, more time equals more fixes or better fixes. In our first place, we try to answer the question, by doubling the time budget of an API tool, do we get twice more possible patches? In order to do that, we give each API tool the same input, the same parameters, and an exponentially increasing time. Here, we give each tool 1 minute, 2 minutes, 4 minutes, and 60 minutes of the time budget, and we count the number of possible patches generated by each repair trial. Given the idea described in the previous slide, and to maximize the diversity of our experiment, we selected 221 bugs from different projects of different benchmarks. For the API tools, we selected 5 different tools from different repair technique families. In particular, we used a Docker version of the repairable framework, and to terminate a repair process at a given timeout, we use a supported Docker kill command. In the next slide, my colleague Ivan Pashchenko will present our results and the analysis of the experiment.
Let me remind you our expectations from the evaluations. If API tools are anytime algorithms, so we expect them to generate the increased number of patches provided they have additional time. And the increase in the number of patches should correspond to the increase in time. For example, if tools have twice more time, they are expected to generate twice more patches. This slide shows the overall number of patches generated by the 5 API tools after running them for 1, 2, 4, and 16 minutes each. As you might notice, after running the tools for just 1 minute, we received 19 patches. Then we doubled the time. If API tools are anytime algorithms, we would expect them to generate 19 multiplied by 2, 36 patches. However, we actually received only 30 patches. Further doubling the time, we observed the bigger difference with the expected number of patches and the actually observed ones. After running the tools for 4 minutes, the expected number of patches is 72, but we observed only 42 patches. So just plus 12 patches in comparison to the number of patches generated after the previous checkpoint. Finally, after running the tools for 8 minutes, we observe only 62 patches instead of expected 144. Hence, exponentially more time means only sublinear increase in the number of plausible patches, instead of expected exponential increase. Since we tested APR tools based on different technologies, let's have a look at their individual performance. The plot on the slide has the time budget that the tools had on the x-axis and the percentage of plausible patches on the y-axis. The highest number of patches was generated by the semantics-based Nepal tool. The tool generated 23 patches in total after running for 16 minutes. Still, this results in around 18% of the total number of patches. We observe that Nepal was able to generate the biggest number of patches in comparison to other evaluated tools. Already after the first minute, Nepal tool generated 11 bug fixes. However, each consecutive increase of the tool's time budget leads to a decreasing number of newly generated patches. +5 after running for the second minute, +4 after 4 minutes, and only +3 after running for 16 minutes. J-Kali tool, based on generate and validate technology, demonstrated similar behavior. The tool generated 5 patches after running for just 1 minute, and then was able only to double the number of fixes, 10 patches, while had 16 times more. GigenProc, NPFX, and Dynamo started slowly. GigenProc and NPFX were able to then produce few more patches. Semantically based Dynamorph tool demonstrated somewhat different behavior. It generated no patches after the first minute. Then the tool demonstrated stepped increase in the number of patches and outperformed the 3 of the related APR tools. As a result, it demonstrated second best result with 15 patches. However, the increase in the number of patches of the Dynamorph tool does not correspond to the exponential increase in the time it was provided. Hence, we observe that every evaluated tool demonstrated sublinear growth in the number of generated plausible patches, given the exponential increase in time. These observations suggest us that if no quick patch is generated by an APR tool, so if no patch is generated within the first 4 minutes, the patch is unlikely to be generated at all. However, in this presentation, we show only the work in progress. For the future work, we plan to run the APR tools on a larger dataset, try other more advanced APR techniques and tools, such as the ones based on machine learning algorithms, and analyze when plausible patches are actually correct patches. All the code and data for replication of our experiments are available on GitHub. If you have any questions and or suggestions, we invite you to contact us. Thank you for your attention.
We are now taking questions. Any questions? Okay. I guess we have a kind of shy audience here. Okay, we have one question. So Bertrand asks, why do you expect the tested algorithm to be anytime algorithm? What changes in this tool's behavior after a while?
Thank you for your question. This work is just our ongoing work, and we, as the we observe some, we experimented some tools, and we observe that there are some tools that do not generate the patches at a given timeout. This is motivation. And as the first phase of the research, we are uh, investigating on the Einstein algorithms, because this is the algorithm that give us the assessment on the time we give to the tools and the quality of the results. And we have not investigated on the tools themselves. The timeout expire. We are just experimenting the tools with the time with given time budget, and then maybe in the future we can dig into the tools themselves, investigate on the internal working of the tools in respect to the time budget.
Mm-hmm. Okay, thank you for the answer. I think the answer more focus on what is the original motivations on the when you started on this investigation on asking these questions, whether it's an anytime algorithm kind of.
Yeah. As presented in the presentation, the motivation is to understand that it makes sense to wait longer for a tool to generate a patch, because the developers time are precious, and uh, we are we need an assessment to understand that if the tools give the patches um, at a time budget that that satisfy the developers expectation.
Mhm. I see. Yes, I agree that this is a natural questions. We have more questions from the audience. So the other questions from Esma is that, hi, do you think that more time equals more patches equals more plausible patches? How can we access this?
In our setup, we consider only the possible patches, and we count in the experiments. We counted the patches generated by the tools only. We have not done the assessment of the patches themselves. We just consider that okay, the tool generates a patch, and in the setup just um, uh, we just stop where we just stop where the tools generated the patch, the first patch, just like counting the number of patches generated by the tools.
Mhm. One more questions. I think like